Hi, in this presentation we're going to talk about multiple regression, which is chapter 3 in our textbook and our third assignment section. Our first slide here is the motivation for what we're doing. You have been up till now working with a regression model that was explaining a response variable y with one predictor variable x1, and we had a simple linear regression model like this where there was a straight line mean function relating x1 to the response. And the issue we're going to try to be careful about in this topic, in this chapter, is what happens, how does it work when you add a new predictor variable to the mean function? And so we'll be talking about mean functions like this, where there is an intercept beta naught, beta 1 is the effect and multiplier for the variable, the predictor variable x1, and beta 2 will control the impact of predictor x2. So really the crucial issue that we're going to be spending time on is how does the additional variable x2 explain y variation that hasn't already been explained by x1. Our motivating data example is going to be some fuel consumption data from 2001. There's going to be gasoline sold, income. The data cases here are going to be states in the United States, and so we have information about fuel consumption, income of the state, how many miles of federal highways there are, the population of the state, tax, and state name. And this is just some of the information in the Fuel 2001 data frame, which is in the ALR4 library. So to make use of this, you'll see in the overheads and in the R commands we have the ALR4 library invoked. It's Fuel 2001 is our data frame, and we're going to create some new variables. One of the new variables we're going to create is a variable called DLIC, and that's basically, if you look at the definition, it's the number of drivers divided by the population. It's basically the fraction of the population that is a licensed driver. Fuel is a new variable derived from fuel consumption, and if you look at it, it's the total fuel consumption in a state divided by its population. So this is going to be fuel consumption per person. Income is going to be a slight rephrasing of the income variable, so that income is going to be in thousands of dollars. And we're going to take a transformation of the federal highway miles and take the logarithm base 2 of that, so we create a new variable called log miles. Here is a way to extract just part of the Fuel 2001 data set. I'll be taking the 7th, 8th, 3rd, 10th, and 9th variables, tax, driver's license, income, log miles, and fuel, and we'll make a new slightly extracted data frame called little f, and we'll summarize little f with summary statistics so you can see what some of the values and the ranges are. And we have a correlation matrix right down here at the bottom. COR of the data frame f means that we're going to be calculating the correlations of all the values in this data frame with all others in the data frame, printed out to 4 digits to the right of the decimal place. The way you would read a correlation matrix like this, for example, the first row is the correlation of the tax, cents per gallon tax in a state correlated with tax, and so that's a perfect correlation of 1. Tax correlated with the fraction of licensed drivers in a state is a slightly negative correlation. Tax is more heavily correlated with fuel consumption. You'll notice that that is a substantially bigger negative correlation. and so forth throughout this matrix. It computes every pairwise set of variables, the correlation for it. So for example, you can see that fuel consumption per person is positively correlated with the fraction of licensed drivers and the logarithm of mileage. This is a basic summarization of a data set. Another very basic summarization of a data set is a scatter plot matrix. And so what I've done here is I've created pairwise scatter plots with fuel consumption, income, tax, and DLIC and log mileage. I have a smoothed mean function traced out in red, and I have chosen to not put the least squares summary regression line on these plots. And what you can see from this scatter plot matrix is that, for example, fuel consumption is very correlated with log of mileage. You can see there's a strong upward correlation there between fuel consumption and mileage. States that have more highways in miles, more highway miles, they tend to have higher fuel consumptions per person. Whereas, for example, this scatter plot suggests that states with higher miles of highway tend to have lower incomes. There's a slight evidence of a downward pattern here. Something like this scatter plot between tax and DLIC almost shows no increasing or decreasing mean function, almost no relationship between those variables. Along the diagonal, you can see the smoothed histograms for each of these variables. So for example, DLIC almost looks like a normal distribution, but log mileage has some evidence that it's skewed to the left. And this gives you an idea about how to visualize the relationships between the variables in this data set. So let's think about the problem that was motivating us. Let's think about trying to explain fuel consumption per person with the state's income. This is basically this part of the scatter plot matrix right here. It's the plot in the first row in the second column. And here it is displayed a little bit more clearly with the best summary line put in over the top of the display in the scatter plot. And you can see there's some evidence for a downward trend. States that have higher incomes tend to have lower fuel consumption, gasoline consumption per person. It's not a very strong pattern. R squared is only about 21-22% of the variation of fuel consumption being explained by income. Here is the equation of the best fit least squares line going through the scatter plot. You can see a negative slope with respect to income. Let's think about explaining fuel by the logarithm of mileage. Here's the scatter plot for fuel and mileage, and you can see for this one there's a little bit of a upward pattern. States with more mileage tend to have a little bit more fuel consumption per person. The relationship is not strong. It's an R squared of about 0.17, 0.18, and you can see the positive upward slope of the equation of this best fit line. So what we've seen in overhead 10 and overhead 9 is using one variable, income or log mileage, to explain fuel consumption. And you can see that it does, those variables, income and mileage, log mileage, do explain some variation of fuel consumption, but not that much. And the question will be, what will happen if you add the variable log miles to a model that already has income, or adding income to a model that already has log miles? And what we're going to find is that the R squareds for the two variable multiple regression model are not going to add together. They're not going to be the sum of 0.2157 and 0.1781. And the reason they're not going to add together is because income and mileage are related to each other. There's overlap in what these variables do together. You can see there is some relationship between income and miles. And that means that when we put both of those predictors together in a multiple regression model, we're not going to get a simple extension of the simple linear regression results. So when we add a predictor, what's going to happen? Well, the second bullet shows us and explains that part of the variation that the second predictor x2 is going to explain, or could have explained, is already going to be explained by the predictor that's already in the model, x1. The way we can get a better handle on this overlapping variation explanation is through a graphical technique called an added variable plot. And an added variable plot is a two-dimensional display. The vertical axis is going to be some residuals, and the horizontal axis is going to be a set of residuals. The vertical axis set is going to be the residuals of trying to explain the response y with the previous single predictor x1. So what's going to be on the vertical axis is the unexplained part of y after x1 has done its explaining the best it could. The horizontal axis is going to be the unique part of x2, the new variable that we're thinking about adding, that hasn't already been explained by x1. So we're going to make a model that has x2 as the response variable, and we're going to use x1 to explain x2, and we're going to take the residuals from that strange regression, and that will be on our horizontal axis. So therefore, in the final bullet, an added variable plot is going to show a visualization of the response variable variation that can be explained by the additional variable x2 after x1 has already done what it can. And here is the picture of an added variable plot for adding log miles to a model that has already had income in it. Notice what we do up in R is we make a multiple regression model that explains fuel as a adding function of income and log miles, data frame fuel 2001, and we use the AV plots command on this MLR2 model object. We'll take away a plot that would be produced if we didn't do this. The terms take away income added variable plot just lets us focus on the added variable plot for log miles. The ID n equals 3 means give us state and data labels for some of the more unusual states. So states that are all off on their own are given labels according to this ID command. So what you can see from this added variable plot is that there is a trend between the two sets of residuals. The unique part of log mileage is correlated and related to the leftover variation of fuel consumption after income has done what it can. You know, you can think about this in terms of, you know, a household or a pizza party or something. Income has gone in and consumed the variation in the fuel consumption pizza, and the question is, will log mileage have anything left to explain? Will it be able to consume some useful variation? And it looks like there is a trend. And this would suggest whenever there is a notable upward or downward trend, it suggests that the candidate variable that you're thinking about adding to the model, in this case log miles, is going to be helpful in explaining the leftover fuel variation. And so that's what we are talking about here in this overhead 14. there is going to be some variation that hasn't already been explained by the income predictor. Remember, the income predictor explained about 21 or 22% of the variation. The horizontal axis is the unique portion of the variation in log miles that hasn't already been explained by the income, and because there's a trend, it is suggesting evidence that this predictor, log miles, is going to explain fuel consumption. If we would not take away part of the display, here's what the plain added variable plots command would produce without any additional options. It would produce an added variable plot for each variable after the others. So you've seen this plot on the right previously. This is for adding log mileage after income. The added variable plot on the left is for adding income after log mileage. And you can see there that there is a downward trend, but it's clear, suggesting that the effect of income is that states with increased income have reduced fuel consumptions. For mileage, it's the other direction. But there does seem to be some relationship between these two sets of residuals, suggesting that each variable is going to explain a notable amount of fuel variation after the other. And that's what is being said here in overhead 16. So keep in mind that the crucial issue is in added variable plots. Do the points suggest an upward or downward trend? No trend at all, or a shapeless pattern centered basically around 0 would suggest that the new added variable is not going to explain variation, and there's really not any additional variation for it to explain. That's what a horizontal pattern would mean. And now we get to the multiple linear regression model. When we have predictor pieces of information x1 to xp, the multiple regression model has a mean function, an average or expected value of y given a predictor set x is this nice linear function of beta parameters and predictor variables. If you know the values for the pieces of predictor information, you can supply a observed or a candidate set of values, little x, and you can plug the variable values into the mean function, and you can express the expected value of y like this. Mathematically and geometrically, this kind of equation is the equation or function of a plane or a hyperplane. It's some sort of flat surface in higher dimensional space. The parameters, beta naught to beta p, are the things that control the shape and the tilt and the orientation of that surface, and they control and dictate what's going on in the underlying data creation system for this situation. If certain predictor variables have an impact on the response and on the mean function, their beta values will control what that story is and what's going on. Beta values that are 0 are going to suggest that those directions and those dimensions are not really being used to influence the response variable y. If the dimension of the problem, little p, is just 1, there's one predictor variable, you're working with the simple linear regression model. A formal expression of the data creation system is that individual observations of y get generated by supplying values for each of the predictor values, and then there is random error producing scatter and variation above and below the mean function regression surface. Another way to write that is that a y observation is just a mean function value with random error above and below it. And this randomness, the random error pieces, is what produces variation around the mean surface. Here's kind of a picture of what we're talking about. Here is a simple two-dimensional two-predictor problem where little p is equal to 2, and there is a plane beta naught plus beta 1x1, beta 2x2 regression surface, and the definition for this surface is an intercept beta naught of 30, a beta 1 value of 5, and a beta 2 value of 7, producing a mean function or a regression surface like this one. And then random errors will produce y values on this vertical axis that are above or below the surface. This is a visualization of what we're talking about. And this is the kind of mechanism that we think will generate our real observed data. Something like this. The job of the statistician will be then to estimate these beta parameters and make decisions and inferences about what we find. The multiple regression model has very similar assumptions to what the simple regression model had. On average, these error innovations in random variables have an average of 0. I'm not saying that every one of them is 0. I'm saying that on average, over the entire collection of these errors, they average out to be 0. Some of them are positive, some of them are negative, but on average they're 0. The variance function for these errors is that they're constant. The standard deviation is sigma. The variance for these errors is sigma squared. It doesn't matter what predictor values x are involved or which data observation we're talking about. The variation is constant for all observations. Third assumption is that the errors are independent for different observations. And then we have the sometimes assumption of normality that gets used for the formulas for confidence intervals and tests, but is not a terribly big concern frequently when we have big samples. In this material, we start to get a lot of observations and a lot of variables, and we need some additional mathematical notation to keep track of what's going on so that we can write expressions conveniently and compactly and that we understand what they mean. So for the most part, our class does not use a lot of matrix and vector notation, but it does come in handy, particularly for cases like this. So I want you to think about all of the response values for our response variable. Remember, in the little example we were using, it's the fuel consumption per capita or per person each state. So we will have Y1, the fuel consumption for the first state, say Alabama, and the last state's fuel consumption is Yn. And we can represent all of those observed response values in a big, long ordered list called a vector, and we'll call all of those y values a uppercase Y for the entire collection. We can think about the predictor variables, x1 to xp, as columns. So if we have a predictor variable, say like income of a state, that will be representing a column in this overall data predictor matrix X, capital X. Maybe another predictor variable like log mileage would be represented by the second column in this X matrix. And any other predictors up to the pth one will be represented by a column. The rows of this matrix represent observations or data points. You'll notice we go from the first row down to the nth row, and our columns take care of all of the predictors we have from 1 to p. We have a column of 1s because in our multiple regression model, we have an intercept. And this is basically the set of values that multiplies the beta naught parameter. We can make a list of our beta parameters from beta naught up to beta p. And we'll collect all of those beta parameters in a list called beta. We can collect all our random errors that generate variation in a vector or a list. The first data observation's random variation is E1, and the last observation, that the error that was used to create it, is En. And that means that you can write the multiple regression model like this. And so this is just a matrix representation of what we had right here on overhead 18. A Y observation is a linear combination of the betas multiplied by the associated x's plus some random error. Well, how can we write that more compactly with everything all at once? And you can do it using this notation in overhead 25. The list of Y values gets to be the way it does in the data creation generating mechanism by the predictors multiplying the beta parameters plus random error. And that gives us our observed data Y and connects it to the random error process, the E's, and the betas. This is our written mathematical statistical expression of the data creation process. Regression problems typically begin with information and variables that we think might be related to the response variable, and these things are called predictors. And so predictors can be continuous variables like income. They can be quantitative discrete variables like the number of cars you own or the number of accidents or marriages you've had. They can also be category variables like marital status or agree or disagree. And so from these predictors, we typically make another set of information out of them called regressors that are going to be the X variables that we talk about in our models. So now we're going to talk about the distinction and how we get from predictors to regressors. So one example of a regressor is the intercept. It's just a column of ones in that predictor X matrix, and that is basically what controls that we have an intercept. Probably the easiest type of regressor is just a raw predictor variable like income from our fuel data set. Other times we might alter or transform a predictor variable like our regressor log of miles, log base 2. Here is a case where our original predictor was miles, but we modify it with a logarithm transformation to make a new variable a regressor that can be used in regression models. Sometimes we might have relationships between a Y variable and a predictor that are curved in some fashion. And maybe a polynomial function might be a good idea for trying to explain a mean function relationship. And in this case, you might also use a regressor, the square of x, or maybe the cube of x, x to the third power, and you might use a model that has x and x squared and x cubed to model a function. And in this case, x squared and x cubed are also regressors. Sometimes we might want to combine two predictors to make a brand new one, a new regressor, like a product, and this would be called an interaction. And so you might make a new variable, a new regressor, which is x1 times x2. This is going to come in very handy when the effect of one predictor, the effect on a response y, might depend on the value of another predictor x2. When we have category variables like agree, strongly agree, disagree, these category variables are also called factor variables. And what we will do is we will handle them by making a series of 0, 1 binary variables that will let us fully define which category an observation belongs to. Regression splines are another way to handle curved relationships between responses and predictors. We'll study those in our class. And when many predictors are available, but they're frequently very correlated with each other, it's sometimes helpful to make sets of correlated items and do a principal components analysis, which basically creates a much smaller number of uncorrelated variables from a very large set of correlated variables. And we'll learn how to use principal component variables in this class as well. So our multiple regression model is defined like this. The mean function is involving the predictors x1 to xp, or regressors x1 to xp. The beta parameters control the story about how these predictors affect the mean function. Our variance function is a constant. And what we need to do in our data analysis is we need to find estimates for the betas and this sigma from our observed data. And we're going to do something very similar to what we did before. We are going to find the residuals. We are going to come up with beta parameter values which minimize the distance between our observed y values and our predicted ones. So we will search through the beta parameter space to find a surface that is as close as possible to our y values. And so we will minimize this set of squared residuals, either expressed like a summation here, y minus y hat, or predicted y squared. You could also express it in terms of vectors. This is a vector transpose the same vector, which means you're going to multiply every element times itself, making this sum of squares. And so this is our task for estimating the multiple linear regression model. And we're going to do that through least squares, ordinary least squares estimation. And it turns out there are some very standard formulas for coming up with our best estimates for the betas. Beta hat is this complicated function of our predictor information and the response data. If you want to think about that a little bit more carefully, what it means is that our estimated y vector is this matrix H, which is called the hat matrix, x times x transpose x inverse, x transpose y. This is a lot of linear algebra, which I don't really assume that you know, but if you do know some linear algebra, you might recognize this as an orthogonal projection matrix. If you don't know what that is, that's okay. If you do know what it is, now you know why you spent so much time studying it in your math course. Anyway, in terms of this matrix notation, we can come up with an expression for our predicted values of y. And if we have the predicted fitted values of y, we can come up with residuals. We can come up with residual sums of squares. And that means we can come up with a guess for our estimated value of sigma. It's just the residual sums of squares divided by the degrees of freedom for this full model, which is always n minus the number of beta parameters. Remember, you'll have p beta parameters for beta 1 up to beta p, and you'll have one additional one for the intercept. Here is the linear algebra and the geometry of what we are doing in this problem. Here is the visualization of the y vector of measurements in high dimensional space. And what we are doing when we use this H hat matrix is we are projecting, and we're taking this y vector that's hanging out there in space and dropping a vertical line down to a space defined by the X matrix. And so that produces this estimated y vector. So we are trying to find the place in this yellow space that is as close as possible to this y vector. And the place that is the closest is right below it, the orthogonal vertical projection of that vector down onto this space. You can think about it shining a flashlight on this pencil that's hanging out here in space, and the shadow down in this surface is the best we can do. This particular overhead 32, is doing some of that linear algebra to show and demonstrate these computations that are here on overhead 30. And I just want you to notice that the beta hat estimates vector is given right here on the very bottom of overhead 32, and I want you to notice that that is exactly the same as what you will get when you use R to estimate this particular multiple regression model. And in our next YouTube video, we're going to go over the properties of the estimates.